Welcome everyone to our highly anticipated panel discussion on terahertz imaging and therapy. Today, we're going to be observing a picture of terahertz technology, eliminating benefits, challenges, and profound relevance across various fields. Terahertz imaging and therapy are at the core of technological innovations, offering transformative applications in medical diagnostics, early detection, and treatment of disease. Its ability enhances screening and safety track detections, and in material science, providing unparalleled insights into material properties. Our esteemed panelists will navigate us through the fundamental concepts underpinning the terahertz technology, its current and emerging application, cumulative impact assessment, and potential capability to mitigate any adverse effect on society and environment. Thank you for joining us in this enlightening exploration. Let's commence our discussion with our first topic, technology, electromagnetic field and wave in terahertz imaging and therapy. So we'll have Mr. Ansika and MRI technologist Mr. Ang. Could you please identify how terahertz imaging and therapy utilize electromagnetic field and wave in its application, and discuss the fundamental concepts of electromagnetic field and wave in the technology?
Okay, thank you for the introduction. One specific technology that makes extensive use of electromagnetic fields and waves is terahertz imaging and spectroscopy. Certainly, terahertz imaging technology relies on a combination of electromagnetic principles to produce detailed images of the body's internal structures. The terahertz imaging system generates a terahertz electromagnetic wave, typically between 0.1 and 10 terahertz, using specialized sources and detectors. In addition to the terahertz wave, smaller variable terahertz fields may be applied in 3 dimensions X, Y, and Z. This variation in terahertz field strength allows the terahertz system to localize the signal to specific areas, enabling the creation of 3D images. Terahertz pulses are used to generate short bursts of terahertz energy at specific frequencies relevant to the material being studied. This terahertz energy temporarily disturbs the molecule's alignment, leading to changes in the terahertz signal's characteristics. After the terahertz is turned off, this released energy is detected by the terahertz detectors, and the 2 main types of relaxation occur, which is T1 longitudinal relaxation and T2 transverse relaxation. The signals emitted during relaxation are converted into images using mathematical algorithms, primarily the Fourier transform, which relates the frequency and phase transform information of the signals into spatial information, producing detailed images of the internal structures. Terahertz imaging is particularly valuable for imaging materials with low water content, such as pharmaceutical, tablets, plastics, and textiles. Terahertz imaging can identify subtle defects and contamination that are not detectable by other imaging techniques. It is also used for security screening and quality control in various industries.
I would like to ask Mr. Ansupyo, how does terahertz imaging compare to other imaging technologies like MRI in terms of resolutions and safety?
Wow, it's a good question. In terms of resolution, terahertz imaging offers high resolution capabilities. Especially for surface or near-surface structures, it provides detailed images without the need for ionization radiation, making it safer. Compared to MRI, which offers deep tissue imaging with excellent resolution, terahertz imaging is more limited in penetration depth, but is advantageous for applications requiring surface imaging and analysis. The non-ionizing nature of terahertz makes it a safer option for frequent or long-time use.
Thank you, Mr. Ang, for the valuable sharing, and also Ms. Lee for the engaging question. So now let's explore the future review and applications of electromagnetic fields in terahertz imaging and therapy. This technique offers insights into current research and practical implementation of terahertz technology. We'll have Ms. Jimmy, an expert in electromagnetic field research with us. Ms. Jimmy, could you provide us an overview of the terahertz imaging and therapy and how electromagnetic fields are utilized in this technology?
Thank you, and I'm happy to be here. Terahertz imaging has shown great promise in the field of medical diagnostics, especially in detecting cancer. Terahertz waves can differentiate between healthy and diseased tissue. They are highly sensitive to water content, which is usually higher in cancerous tissue compared to healthy ones. This makes terahertz imaging particularly useful for detecting tumors. Photoconductive antennas use a material like gallium arsenide. When illuminated by a very fast laser pulse, this material generates electron-host pair. Applying a bias voltage makes this pair move quickly, producing terahertz radiations. In optical rectification method, special crystal convert ultra-fast laser pulse directly into terahertz radiations. Time domain spectroscopy (TDS) technique is used to detect the terahertz pulse. The generated terahertz waves are measured over time to produce a signal. By analyzing this time domain signal, we can obtain important information about the tissue, such as its refractive index and absorption properties. This helps in distinguishing between healthy and cancerous tissue. Studies like the one by Woodward et al. 2002 have shown that the terahertz imaging can effectively distinguish between cancerous and healthy skin tissue. This is extremely useful for skin cancer diagnostics, where detailed surface imaging is crucial. Thank you for the attention.
I'm sorry for this. Ms. Jenny, what are some potential challenges or limitations of terahertz imaging in medical diagnostics?
Okay, for the potential challenge of terahertz imaging in medical diagnostics include the need for precise and expensive equipment, potential difficulties in imaging deeper tissue due to limited penetration depth of terahertz wave, and the need for further research to standardize and validate the technology for widespread clinical use.
Thank you, Ms. Jimmy and Ms. Alisa, for the amazing questions. So now I'd like to invite our panelist, Ms. Alisa, an environmental health specialist, to provide an analysis of the impact of the chosen technology on health and the environment. Ms. Alisa. Please provide an analysis of impact of the chosen technology on health and our environment. So let's delve into the impact assessment on both health and environment for terahertz.
Thank you, Ms. Zindi, for asking me that question. The terahertz imaging and stereoscopy are imaging technologies with significant potential for medical diagnostics and material characterization. Their impact on health and environment is generally considered positive. For health, the waves are non-ionizing radiation, meaning they don't carry enough energy to damage DNA like X-rays. This makes them a safer alternative for imaging purposes, particularly for sensitive tissues. Terahertz imaging can potentially detect cancer, monitor wound healing, and identify other health issues without the risk associated with traditional methods. While for environment, terahertz technology itself doesn't produce harmful pollutants or byproducts. However, the environmental and health impact of terahertz technology needs further investigation. Overall, terahertz imaging and spectroscopy offer a bright future for healthcare and scientific exploration. Continued research is crucial to ensure its safe implementation and minimize any potential environmental drawbacks.
Sorry, Ms. Erica, I have a question. Given these potential risks, what measures are currently in place to minimize the negative impacts on patients and environmental?
Thank you for asking that interesting question. Terahertz imaging and spectroscopy, while boasting exciting possibilities in healthcare and research, come with potential risks related to electromagnetic field, EMF, exposure, and environmental impact. While terahertz waves in themselves are classified as non-ionizing, meaning they don't possess enough energy to directly damage DNA, the long-term effects of chronic low-dose exposure remain under investigation. This is particularly concerning for medical applications where patients might undergo repeated terahertz scans.
Thank you, Ms. Erica, and thank you, Ms. Suren. So now I'd like to invite our next analyst, Ms. Suren, a regular compliance officer, to address the potential negative impact on terahertz technology might have on society and environment. Ms. Suren, could you discuss the possible solutions of how to improve the safety measures and evaluate regulatory efforts and also those technological innovations to mitigate this problem?
Thank you, Ms. Cindy. As we explore the potential of terahertz imaging and spectroscopy, it's crucial to address their potential negative impacts on the society and environment. To balance the benefit and the risk, I propose improved safety measures, robust regulatory frameworks, and innovative technological advancement. Firstly, while terahertz radiation is non-ionizing and generally set at low power levels, prolonged exposure could pose risks. Comprehensive safety guidelines, regular training for the personnel, real-time monitoring, and the automated shutdown mechanism are essential. Secondly, the environmental impact of the terahertz technology, including the electronic waste and the energy consumption, must be mitigated. Green manufacturing processes, environmentally friendly materials, responsible disposal, and recycling strategies are key. Improving energy efficiency is also important. International regular standards and collaboration with the organization like the International Commissions on Non-Ionizing Radiation Protection are important. Governments should create regulatory bodies to ensure the compliances. Technology advancement can reduce the risk, and the advanced materials, better shielding design, and improve the detection techniques and the non-contact sensing methods can also enhance the safety and the efficiency. And lastly is the public awareness and the education are also important. We can have a campaign to inform the people about the benefits and the risks of the terahertz technologies. Transparent information and the community engagement can build the trust and address the concerns. And that's all from me. Thank you.
Wow, thank you, Ms. Yuan. What a wonderful detailed overview. My question is, regarding the implementation of advanced materials and designs to reduce exposure risk from terahertz radiation, could you please elaborate on some specific materials or design innovations that show promise in enhancing safety in terahertz technology?
Sure, and thank you for your questions. Innovation in material and design are crucial in enhancing safety in the terahertz technology. Developing metamaterials to block and absorb the terahertz radiation can minimize the exposure risk. And additionally, composites integrating methods with the polymers offer better shielding while maintaining the flexibility. Optimizing the layout and the structure of the terahertz components to minimize the radiation leakage is also important. Advance in the manufacturing allow the precise control over component placement and the use of the isolation measures to prevent the unintended exposure. Combining these strategies significantly improves the terahertz technology safety and ensuring the effective use while protecting operators and the public from a potential risk.
Thank you, Ms. Yuan. And so today the discussion on terahertz imaging is going to highlight the significant role in various field and implications for health and environment. Terahertz technology will grounded impact applications in medical diagnostics, security, and material characterization. Utilize the electromagnetic field to penetrate molecular and provide deeper impact. While radiation is generally at low power levels, ongoing research is crucial to understand any potential long-term effects alongside addressing environmental impact, long manufacturing processes, and energy consumption. Mitigation strategies discussed including implementing safety measures, regulatory frameworks, technological innovations in public and awareness campaigns. Moving forward, the research on the health effects of new innovations to the energy efficient and sustainable technologies are essential. In conclusion, terahertz technology imaging and photography offers immense opportunity for scientific advancement, and for advertisers will ensure their safe and sustainable use. Thank you all for your contributions as we strive to enhance our life with terahertz technology while safeguarding health and environment. Thank you.